Okay guys, I welcome you all to Engineers Academy. Do subscribe my channel for the solution of such more problems from Engineering Statics by Meriam and Kraige. This is chapter 3, problem 88. The problem says that the uniform 15 kg plate is welded to the vertical shaft which is supported by bearings A and B. Calculate the magnitude of the force supported by bearing B during the application of the 120 Newton meter couple to the shaft. The cable from C to D prevents the plate and shaft from turning, and the weight of the assembly is carried entirely by bearing A. So we are given this plate which is welded to this shaft, and this shaft is subjected to this 120 Newton meter couple, and the rotation of this plate is prevented by this DC cable. So first of all, we have to define our coordinate system, our reference coordinate system. So let's say that my x-axis is acting from the shaft in the outward direction like this. Let's say this is our x-axis, and let's say my origin is at point A. So let's say this is my reference x-axis, and then our y-axis is in this direction. Let's say this is our y-axis, and the z-axis is along the shaft. This is the z-axis which is acting in the upward direction. So this is our z-axis. So now this means that the shaft is along the z-axis. Now the first task in this problem is that we have to find the Cartesian vector representation of the tension in this cable. So let me represent the tension we will have if I cut this rope. So we will have the tension in this cable, and that tension is going to act in this direction. This will be our direction of the tension. Let's say this is represented by T. This is T vector. So now first of all we have to find the T vector. So T vector, this is always equal to that magnitude of this T times the unit vector from D to C. And now we can write that this is T magnitude, and the unit vector from D to C is the position vector from D to C divided by the magnitude of that position vector. So now we have to find the position vector from D to C. So let me write that this is T, and we can find the position vector by moving along x, y, and z from D to reach that point C. So now from D we need to travel in this direction, that is in the negative x, from this point to this point, right? We have to travel 600 mm distance in the negative x direction. So 600 mm divided by 1000 will give us 0.6 meters. So we have to travel 0.6 meters from D in the negative x direction. So I will write that this is 0.6 in the negative x. So in the negative x we mean that we need to move in the negative I direction. So we will reach here, and then once we reach here we have to travel this distance in the negative y direction. This is our positive y, so we have to travel 200 mm. So 200 mm divided by 1000 will give us 0.2 meters. So we have to travel 0.2 meters in the negative y. So I will write minus 0.2 in the negative j. So this is the position vector from D to C. Let me write it like this. And now we have to find its magnitude. So its magnitude will be 0.6 square plus 0.2 square under the square root. So let me find this magnitude. This will be 0.6 square plus 0.2 square. This gives us 0.632. So this is equal to 0.632 approximately. So now we can write that the Cartesian vector representation of the T vector is equal to this T, and now we need to divide each component by this magnitude. So we can write that this is minus 0.6 divided by 0.632 in the I, and then minus 0.2 divided by 0.632 in the j. So this gives us, this is T magnitude, and now 0.6 divided by 0.632. Sorry, this is 0.949, right? So this is minus 0.949 minus 0.2 divided by 0.632. This gives us 0.316. So 0.316 J. So this is that Cartesian vector representation of that tension in DC cable, which prevents the plate from rotation about the z-axis. So this will be in newtons. Now we have to find the magnitude of this T. So to find the magnitude of this T, we have to consider the top view of this whole mechanism, right? So if I observe this plate along with the shaft from the upward direction, that is the top view. So we will have this as a free body diagram. Let me put that free body diagram. So let's say this is our free body diagram. We are looking to this whole mechanism from the top. So this is that support, this blue is that support, and this is that plate, and this is that point D, right? So this tension T is from this point D to somewhere here, right? This is that tension T, and these are the two components of that tension. So we want to find, let's say this is, since if I draw the x and y axis, so our x axis is, if we are looking from the top, so our x axis is, this is that point A, so this is our x axis, which is acting from this point towards the D, and then our y axis is, this is our y axis, which is parallel to this edge, So this is our y axis. So now as we can see that this is the y component. We can write that this is the y component of that tension T. This is T. So this is the y component, and this one is the x component. So now from this we can write, from this equation we can write that this T vector, this is equal to minus 0.949 T I minus 0.316 T J, and this is in newtons. So now if we look into this, so as we can see that this T is passing through that point A. Let's say this is that point A. Let's say this point is that point A, and let's assume that this Tx is passing through that point A, since we can neglect the thickness of this plate. So if we neglect the thickness of this plate, so then this Tx is going to pass through that point A. We can say if we neglect this thickness, so the moment of this Tx about that point A will become 0. So we can say that this Ty is only producing the moment about that point A. So now if this is the top view, let me write that this is the top view. So if we consider the top view, then we can say that we have that couple about the z-axis is like this. This is how much. This is 120 Newton meter. This is that couple, right? So if we apply the summation of moment about point A equals to 0 in the top view, and if we assume that the counterclockwise moment is positive, so now as we can see that this couple is the counterclockwise moment. So we will write that this is plus 120, and the moment produced by this Tx is 0, so Ty is producing the clockwise moment about that point A. So I will write minus Ty, and the perpendicular distance of this Ty from that point A is this distance from here to here, So this distance is the length of this plate. So this distance is 600 mm, or we can say that this is 0.6 meters. So I will multiply this with 0.6 meters, and this is equal to 0. So now if I bring this Ty term to the other side of equation, so this will give us Ty equals to 120 divided by 0.6. So 120 divided by 0.6, this gives us 200. So Ty comes out to be, this is 200 newtons. And now from here we know that this is Ty, this is 0.316 T. This is the magnitude, this is only the magnitude, right? So we will write that Ty is, we can write this 0.316 T equals to 200, and since we want to find T magnitude, so this will be equal to 200 divided by 0.316. So this answer divided by 0.316, this gives us 632.91, right? So this T is equal to 632.91 newtons. So now if you want to find a Tx, this is that Tx. We can write that Tx component of that tension T. This is equal to minus, let me write, we want to find only the magnitude. This is the magnitude, remember. This is Tx magnitude and this is Ty magnitude. We are not considering the direction, right? So Tx is 0.949 into T magnitude, which is 632.91. So this is equal to, now we have to multiply this answer with 0.949. Oh, this is 0.949 multiplied by 632.91. So this gives us 600 approximately. Let's say that Tx is 600 Newton. So now we can write that this is 600. Now we can write that T Cartesian vector is equal to, so Tx is 600, this is acting in the negative x, and minus Ty is 200 J. So this is the tension T in that DC cable which prevents the plate from rotating about the shaft. Now in the problem statement we are asked to calculate the magnitude of the force supported by the bearing B. Right, so at bearing B we will have two reaction forces. We will have By reaction which is going to act in this direction. This is the assumed direction. Let's say this is By which is acting parallel to the y-axis, and here we will have Bx which is going to act parallel to the x-axis. This is my Bx, and at A we will have reactions as well. Let's say here we will have Ay, and here we will have Ax. Now we were asked to find this Bx and By, and we have to find the magnitude of the force supported by bearing B. So we have to find the total reaction or the total supported point B. So we have to find Bx and By, and then we have to find the magnitude of that total reaction. So for that we have to consider again the approach which I am following is the scalar approach. Remember, this is we are solving this whole problem by scalar solution. Remember, we are not considering the vectors, we are considering the R into F formula for finding the moments. So this is the scalar approach, remember. So now to find that Bx and By, the whole task is to find Bx and By. We have to consider the front view. Let's say if I observe this whole mechanism now from this side, and let's assume that from this side we will be able to see the front view, and from this side we will be able to see the x and z axes. We will be able to see the xz plane, and similarly if we observe this whole mechanism from this side, we will be able to see this y and z axis. So we will be able to see the y and z plane. So now these are our two orthographic projections. This is the one is the front view, this one is the front view. Let's see, this is my front view, and if we look into this whole mechanism from this side, so that will be our right side view, right? So this one is our right side view. Now let me put these diagrams side by side so that we can compare all these. So this is our front view, this is our front view, and this is our right side view. So now if I draw the components of this T, since we found this Cartesian vector representation, so this T is having minus 600 Newton, we can say the 600 Newton component in the negative x. So if I represent that component, so at point D we will have this component, this is that 600 Newton component, and here at D we will have 200 Newton component in the negative y. This is in the negative x and this is in the negative y. This is minus 200 and this is minus 600. So here if we, in the front view, we will be able to see this 600 Newton, right? This is 600 Newton. 200 Newton is out of the screen in this front view. Similarly, this Bx, we will be able to see this Bx, which is parallel to the x-axis. We will be able to see the x and z-axis if we observe this whole mechanism from this side. So this is the xz, this is the xz plane, and we will be able to see the Bx component and Ax component. And the By and Ay components are into the screen. So we are not going to see them in the front view. Similarly, in the right side view, we will be able to see this 200 Newton component, which is parallel to the y-axis. Since we are going to, this right side view gives us the yz plane, y and z-axis. The x-axis is out of the screen. So we will be able to see this 200 Newton. 600 Newton is into the screen, and this we will be able to see this By component, and we will be able to see this Ay component. Ax and Bx, those components are out of the screen, and the weight of this plate is acting in the negative z direction, which we will be able to see like this. And similarly, in the front we will be able to see the weight. The weight is going to act somewhere here like this. So this is that weight, and this weight is 15 times 9.81. Since the mass of the plate is 15 kgs, so the weight is 15 times 9.81. Now if we consider for scalar solution, if we consider the front view, let me write that if we consider the front view, that is the xz plane R projection. So this will be, then we can say that if we apply the summation of moment about point A, since we are interested to find Bx, so we have to eliminate that Ax reaction. So we have to find summation of moment about point A equals to 0, since the system is in equilibrium. So the summation of moment about point A will be equal to 0, and we will assume that the counterclockwise moment is positive. So now as we can see that this Bx is going to produce the counterclockwise moment, so I will write plus Bx, and the perpendicular distance of this Bx from that point A is this distance, which is, from here we can say that this is 200 mm, which is 0.2 meters. So this is 0.2 meters. The distance between A and B is 0.2, so I have to multiply this with 0.2. This is the perpendicular distance, or we can say that this is the moment arm of this Bx. Similarly, this weight is going to produce the clockwise moment about that point A, so I will write minus, the weight is 15 times 9.81, and the perpendicular distance of this weight from that point A is this distance, and this distance is, from here we can say that this distance is 300 mm. Since the weight is going to act at the geometric center of this plate, so if it is acting at the geometric center, then this distance will be half of the length of this 600 mm. So this is 300 mm, and 300 mm in meters is 0.3 meters. So we have to multiply this with 0.3. So I will write that this is 0.3 into the weight. And now this 600 Newton component of that tension T is going to produce the clockwise moment about point A as well. So I will write minus, this is 600, and the perpendicular distance of this 600 Newton force from that point A is this distance. Let me write, this distance is 80. So from here to here, this distance is 80, or we can say that this is 0.08. Remember, this is 0.08. 80 divided by 1000 will give us 0.08 meters. And similarly, this height of the plate is this height of the plate is 400 mm, or we can say that this is 0.4 meters. So now the perpendicular distance of this 600 Newton force from that point A is this total distance. This is 0.4 plus 0.08 plus 0.2. So 0.4 into plus 0.2 is 0.6. So this is 0.68. So I will write that this is 0.68. Or we can say that the distance of this 600 Newton from that point A is this 400 plus 200 plus 80. So this is 680, and 680 divided by 1000 will give us 0.68 meters. So this is equal to 0. Now this is 0.2 bx, and let me calculate this. This is minus 0.3 into 15 into 9.81. This gives us minus 44.145 minus 600 into 0.68. This gives me minus 408 equals to 0. So we can write that this is 0.2 bx, and if we add both of these, this is minus 44.145 minus 408. This is minus 452 minus 452.145 equal to 0. And if I bring this to the other side of equation, so it will become positive, and if I divide this by 0.2, so we will get bx. So 452.145 divided by 0.2, this gives me bx equals to 2260. This is approximately bx is equal to 2260 Newton. Now we have to find that by. Again we have to consider the right side view. Let me write that I am going to consider the right side view, or we can say that we are considering the YZ plane. So this is our YZ plane, and now as we can see, again we have to find the summation of moment about point A. That must be equal to 0 since the system is in equilibrium and the counterclockwise moment is positive. Now as we can see that this By is producing the counterclockwise moment, so I will write plus By, and the perpendicular distance of this By from that point A is again 0.2. This is 0.2, right? So this is from here to here, this is 200 mm, or in meters this is 0.2 meters. So I will multiply it with 0.2, and then as we can see that this weight is going to pass through that point A, so it is not going to produce the moment about that point A since its perpendicular distance from that point A is 0. And the similar case is with AY. AY is passing through this point A, so it's not going to produce the moment about that point A. So this 200 Newton force is producing the clockwise moment, right? So we will write minus, this is the component of that tension T. This is 200, and again the perpendicular distance of this 200 Newton force from that point A is this 400 plus 80 plus 200, so this is 680 mm, or we can say that this is a 0.68 meters, and this will be equal to 0. Or from this we can write that By is 200 into 0.68 divided by 0.2. So this gives us 680. This is 200 multiplied by 0.68 divided by 0.2. This gives us 680. 680 newtons. So these are that Bx and By reactions at B. So the total resultant reaction at point B will be equal to, that is, let's say B, that will be equal to Bx square plus By square under the square root. So this is equal to Bx is 2260 square plus 680 square. So this gives us 2360 approximately. This is 2360 newtons. And if we want to represent that B reaction as a Cartesian vector, then this will be equal to Bx I plus Byj. So Bx magnitude is 2260, and here the plus sign means that it is acting in the positive x direction. Our assumed direction is accurate, right? So this is 2260 in the positive I, and By is 680, so this is plus 680 in the positive j, and this is in newtons. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe my channel for the solution of such more problems from engineering statistics by Meriam and Kraige.